So another way we look at finding relative mins and maxes is we use the second derivative test or use concavity. So let's first talk about a couple of things about what concavity looks like. So the second derivative tells us the concavity. So if you think about the first derivative, remember the first derivative of s tells us whether the slopes are positive or negative. And sometimes we call that increasing or decreasing. So if the first derivative is positive, it's increasing. If the first derivative is negative, it's increasing. If the second derivative is greater than 0, we say it's concave up. And what concave up looks like is it looks like a bowl upward. So a graph that has a positive second derivative is something that looks like this. This has a second derivative greater than 0. Where the second derivative is negative is bowl downwards. Second derivative is negative. If the second derivative is less than 0, then we call this, and we call this concave down. Concave down. And we call this one concave up. Okay? So that's what we mean by concavity, just that it's bowl, kind of downward bowl. So if I have, like, for example, if I make up a graph, right, and I make a graph that does this, then that, okay, then you would say it's kind of bowl upwards. When is it concave up? From here to about here, it's up. Then from here to about, say, here, it's down. Okay. And then from here to about, say, about here or so, it's up. You're just eyeballing it, just graphically. And then from here to here, it's down again. Because, again, you're thinking bowl upwards or bowl downwards. That's the visual way to look at concavity. Okay. Now, this is useful. There's two things that we kind of talk about. Two important things to think about. One is the points where where it changes concavity. These points here, we call them points of inflection. So a lot of vocabulary. Inflection. Points of inflection are where the second derivative changes signs. And so what we're going to do is we're going to do a sign test on the second derivative if we're trying to find that. Okay, so to find points of inflection, or inflection points, okay, what we do is we set the second derivative equal to 0 or undefined. And then we create a number line, which I call is a number line, like we do for the first derivative test. Number line. This is sometimes called a sign test. Sign test for the second derivative x. Almost identical to the way we would run the first derivative test. This is how we're going to find inflection point. So it's basically where the concavity changes. Wherever the second derivative changes signs is when, and that's similar to what we did on the first derivative test. We were looking for the first derivative change signs. That told us relative mins or maxes. When we do the second derivative, okay, of the function, and we do that same sign test, then we're talking about where are there points of inflection? Where does it go from concave up? Where does the sign change for that second derivative there? Okay, the last thing, so that's what we do here. But there's another thing we use a second derivative test for. Second derivative test is for finding mins and maxes, finding relative mins and maxes. Okay. Now, why is that? Why we have the first derivative test? First derivative test is useful. Second derivative test is just another way in order for us to find the find the relative mins and maxes. So step one's always the same. We find the critical points. That's where the first derivative is equal to 0 or undefined, or does not exist. Undefined or does not exist. Okay, the second thing we're going to do is we're going to plug in the critical points into the second derivative of x. Now, why is this useful? So let's take a look at this one here. Right here, we have a min, right? And that means the derivative is 0. If you plug in the second derivative, you should get a positive value. If you get a positive value, that means it's concave up. that means it has to be a minimum. And if you plug in the second derivative and it's downward, it's negative, then that means that it's a maximum. Okay, so let's kind of do the same example that we did. Let's look at this function f of x. This is the same example we did at the beginning when I was teaching you the first derivative test. That's the x cubed minus 3x squared plus 2. So if you recall, let's just go through the test here. So we first find the critical point. So the first derivative instead equal to 0. So this derivative is 3x squared minus 6x equals 0. And we factor out the 3x, we get x minus 2 here, and that's x equals 0 and 2. Those are our critical points. Now we compute the second derivative, the derivative of this guy, which is going to be 6x. And you compute the second derivative at 0, and, 6x minus 6. The derivative of that is 6x, and then derivative minus 6x minus 6. If I plug in 0, I get negative 6. What that tells us is that we know the first derivative is 0, so we know it's a horizontal tangent line, okay? But we also know it's negative, so that means it's concave down, and that makes that x equals 0 a relative max, okay? Let's do the second derivative, but now let's plug in the other critical point, 2. And that is 3 times 2, plug it into the second derivative. That's 6 times 2 minus 6. That's going to be positive 6. That's greater than 0. That means it's concave upward, which makes that a relative min. X equals 2 is a relative min. Now, there's one thing we have to keep in mind here. This is the one weakness of this test. If you find the second derivative to equal to 0, what that tells you is the test fails. That means we don't know whether it's a relative min or max. The test has failed. It fails to give us an answer, and thus we don't know if it's a min or a max. So that's the one weakness. If you plug in the second derivative and you can't find the concavity, it doesn't mean it's neither. It doesn't mean it's not a min, or it doesn't mean it's not a max. It just means that we cannot tell from the second derivative test whether it's a min or a max there. Okay, and so we'll do a few more examples of us finding the points of inflection as well as applying the second derivative test. So now we're going to be looking at concavity and the interpretation of the second derivative. And in general, concavity is kind of the physical interpretation is when the second derivative is positive, we say it's concave up. It looks like this, like a bowl facing upward. And when the function has a second derivative less than 0, it's concave downward, or it's bowl facing downward. Okay, so that's what we're doing. Kind of like the first derivative tells you when a function is increasing, it's ramping up or going downward because the slopes are positive or negative. Concavity doesn't tell you whether it's increasing. It's telling you whether it's bowl upward or bowl downward. So if I have a curve like this, for example, in this area it's concave up, here it's concave down, here it's concave up, here it's concave down. Now, points of inflection are the points where the concavity changes. So, like, for example, on a curve like this, around here, the curve kind of went from concave up to concave down. And then around here, it went from concave down to concave up. See that? So those would be kind of the points of inflection. And maybe another one right here, if I were to extend this, and this was concave down and concave up. Those would be the points of inflection. Points of inflection are where the second derivative equals 0, and the concavity changes between the left and the right point. So kind of like when we were using the first derivative test to find mins and maxes, where a min and a max is where here's a minimum, here's a maximum. It's kind of like I made a number line or an interval where I said to the left it was positive and to the right's negative, or it went from negative to positive. If I'm looking for a sign change, that means the concavity is changing, and hence that is a point of inflection. So that's kind of the logical process we want to take through when we're doing this. So A is find the points of inflection, and then find where the function is concave up and down. You can do these both together by this kind of method. We're going to compute this second derivative, but first we need to compute the first derivative. That's equal to 2x minus 2. Then we need to compute the second derivative. Second derivative is just equal to 2. Okay, so this function is never equal to 0, so there's no points of inflection. And the second derivative, by being 2, it's always greater than 0. always. So it's only concave up, and it's always concave up. Always, sorry, concave up. And if you think about what this is a graph of, this is a parabola, an upward-facing parabola. And it should make sense that it's concave up everywhere. It never looks like a bowl downward for this graph, right? And so that's what analytically we have found. Okay, let's look at this one. First derivative is 3x squared minus 1. Second derivative is 6x. Okay, now sometimes this is going to be positive, sometimes it's going to be negative. The transition point is when it's equal to 0. So that's x equal to 0. So x equal to 0, the second derivative is definitely equal to 0. And so we make kind of a little line like this where I say, well, at 0, definitely the second derivative 0. When x is less than 0 or x is greater than 0. So x is less than 0, what is the second derivative doing? Well, when x is less than 0, this value is going to be negative, right? Because if I do like -1, for example, it's going to be -6. And when it's greater than 0, when x is positive, this whole term is positive, okay? So x equals 0 is a point of inflection. So this is a point of inflection because the concavity changed. See, it changed from concave down to concave up. Okay, this is concave up, this is concave down, because when the second derivative is negative, it's concave down, this is concave up. So in this interval, it's concave up, and this is concave down. Okay, let's look at this one. So first I want to calculate the first derivative. That's going to be, when I multiply by 4, it's going to be 4 over 4, so that's just x cubed. 3 times 3 is, 3 divided by 3 is going to be 1, so it's going to be x squared minus 2. And the second derivative is going to be 3x squared plus 2x. And I want to know when this is equal to 0. Kind of like doing critical numbers for first derivative tests, you're doing critical numbers for candidates for points of inflection here. So I'm going to factor out an x, and this would be 3x plus 2. That's the best way to solve for equal 0, is to factor when you can. And that tells me, well, x equals 0, or 3x plus 2 is equal to 0, because either this is 0 or this is 0. And so this is x is negative 2/3. And so then when I create my sort of my line here, I have a point at 0, or sorry, not 0. From left to right, I'm going to do negative 2/3, and I'm going to have 0. There and there. Okay, so the second derivative is 0 at those points. That's what I've computed. I want to know what happens between here, between these intervals, when x is greater than 0 and x is less than negative 2/3. Okay, so if I go really, really, really negative, this whole thing's going to be a giant positive number. It's going to be much bigger than this, so it's going to be positive. If I'm between here and here, if I look at maybe this calculation, this factored form, if I plugged in like negative, a small negative number close to 0, this is negative, and then this is going to be positive, right? Because if it's like negative, like a quarter or something like that, this is going to be smaller than that one. So this is going to be negative times a positive. That's going to make it negative. And then when I have a very big positive x value, this is positive, so this is going to be positive. Okay? So here and here, it's concave up. Because the second derivative is positive. Here it's concave down because the second derivative is negative. And these two are the points of inflection. These two are points of inflection because to the left the concavity changes. Now we don't make a distinction for points of inflection like we do for for the first derivative test. We made a distinction in like a relative min versus a relative max for classification. For points of inflection, you're only looking for a change in the sign. There's no difference between if it goes from concave down to concave up or concave up to concave down. They are both considered points of inflection. Okay. Let's do the same for number 4. First derivative is going to be 4x cubed minus 12x squared minus 12x minus 4. And so the second derivative is going to be 12x squared minus 24x minus 12. Now I want to know when this equals 0. I can factor out a 12. That becomes x squared minus 2x minus 1 is equal to 0. This should have been plus, I was going to say. And so this factors into 12x minus 1 quantity squared. Okay. And so that only happens at x equals 1. Okay, so that's my candidate. So if I were to plot my line f and f double prime of x, okay, I just have a 1 here. And this is, the second derivative 0 at that point. And if I look to the left, like x less than 1, note that this quantity is always positive. Because no matter, even if this part here is negative, which it would be when x is less than 1, when I square it, it becomes positive. And then 12 times a positive number is still a positive number. And this is also positive. So it's concave up here and in this interval. So the only time it's not concave up is at x equals 1. And for this value, it's not a point of inflection because the concavity didn't change. So this is not a point of inflection. There are no points of inflection. You would say no points of inflection. Okay. Let's look at number 5 here. First, I'm going to write this. To do the first derivative, I write this as x squared plus 1 to the negative 1. And that way I can do power rule with chain rule. You could do quotient rule. Either way is fine. Sort of not just as a personal preference. I like it in this form because it would just make it easy to do the second derivative and multiple derivatives. So first, the outer function is a power, so I got to do power rule. That's negative 1 x squared plus 1 to the negative 2. Leave the inside alone. But because the inside's not x, I got to multiply by the derivative of the inside. And so that's 2x. And so this is, I just leave it like this. I'll make this negative 2 to bring it out here. X times x squared plus 1 to the negative 2. Okay, so when I do the second derivative now, the derivative of this, you could move this down and then do quotient rule. It's not a bad way to do it. It actually would be a little cleaner, but I'm going to show you doing product rule this way because this is what I'm used to doing it. It does require a bit of factoring after you do it, though. So I'm going to keep the negative 2 out, right? So I always do constants separately. So then I'm just going to do the derivative of this and this. And I'm going to do product rule. So I'm going to do x times the derivative of this one. That's going to be negative 2 x squared plus 1 to the negative 3. That's power rule. Then times 2x by chain rule. Because the inside's not x, I got to take the derivative of the inside. Plus the derivative of x, which is just 1, times x squared plus 1 to the negative 2. Okay? And so this is negative 2 times... And what I'm going to do is, so I already have a negative 2 out here, and what I'm going to do is pull out an x squared plus 1 term. And remember with my factoring, I always pull out the smaller one. Negative 3 is smaller than negative 2, so I pulled that out. And what I'm left with here for this one, because I pulled this one out for this term, I'm left with a negative 4x squared. Okay? And then for this term, I'm left with, well, what times this would give me negative 2, an x squared plus 1 term to the first power, because 1 plus negative 3 would be negative 2. And so then I get negative 2, x squared plus 1 to the negative 3, times negative 4x squared plus 1 is negative 3x squared plus 1. And then finally, to write this as a fraction, it's going to be negative 2 times the negative 3x squared plus 1 divided by x squared plus 1 cubed. Okay? And so I want to know when this is equal to 0 for my possible points of inflection. When I write it like this, only the numerator will be 0 is the only way that like this could equal to 0. So then this becomes negative 3x squared plus 1 is equal to 0. That means 1 is equal to 3x squared. 1/3 is equal to x squared. And so x can be plus or minus square root of 1/3. That's really plus or minus 1 over root 3. And if you really like it as rationalizing the denominator, it's root 3 over 3. Because I got to multiply by root 3 over 3 here, right, to get to that. So these are my critical points here. And so now I'm going to have x and f double prime of x here. So my first point would be negative root 3 over 3. Then I'm going to have root 3 over 3. Oh, Let me move that down a little bit. Apologize. Thought I could get that in there. Move it down over here. Okay. And then, yeah, so here I know the second derivative is 0, and now I need to start evaluating what's going to happen here. Okay, well, let's look at the bottom. So this is negative. This part here is always positive because x squared, no matter what, is always positive. So plus 1 will still make it positive, and then I cube it, it's still positive, right? So this is always positive, and this is always negative. So I really have to worry about what's happening here. And if you think about it, the squaring, like let's say I take a really big negative number. I square it, it's going to be negative. So this is going to be negative. When I add 1, it's going to do nothing. It's going to be negative times a negative over a positive. That makes that positive down here. So between here, let's say like 0, for example. So if I plug in 0, this is going to be positive 1, negative, divided by a positive number. So that makes that negative. And then when this is really, really, really big, this again will be negative. This whole thing will be negative times a negative is positive, divided by positive, that keeps it positive. Okay? So when x is less than negative root 3 over 3, it's concave up. Between negative root 3 over 3 less than x less than root 3 over 3, it's concave down because the second derivative is negative, and here it's concave up because the second derivative is positive. And these two are both points of inflection because the concavity changes to the left and to the right of it. Okay. And then let's look at doing this one here. So I want to first find the first derivative of x. Here I'm just simply going to do product rule, the x squared and the ln x. So I'm going to do x squared times the derivative of ln of x, it's 1 over x, plus the derivative of x squared, which is 2x times ln of x. And simplifying this becomes x plus 2x ln of x. Okay, and then I want to take the second derivative of this. Derivative of x is 1 plus 2 times, I'm going to do product rule. See, I do the constants separately. And I do product rule for x and ln x. X times the derivative of ln x is 1 over x, plus the derivative of x is 1 times ln of x. And so this is 1 plus 2 times 1 plus ln of x, because these x's will cancel, and I get 1 plus 2 plus 2 ln of x, and that's 3 plus 2 ln of x. Now, I want to know when this is equal to 0 for my critical numbers. So I have 2 ln x equals negative 3. Ln of x is equal to negative 3 halves. And to get rid of the ln, this is what I would do, is I do e to the both sides. Okay? Because whatever I do to one side, I can do to the other. And the property of e and ln is that they cancel each other. Okay, so that means x is equal to e to the negative 3 halves. Okay, so that's my critical number there. And so now let's look at my number line. I'm going to have x, f double prime of x. This is x is less than e to the negative 3 halves. Then I have e to the 3 halves. Then I have x is bigger than e to the negative 3 halves. Okay, so the second derivative is 0 here. And so when I'm smaller, you could either use a calculator for this. You could say, well, when I'm smaller than e to the negative 3 halves, the ln of that is going to be smaller than negative 3 halves. So let's do like a really giant negative number. The ln cancels with the e, so it's going to be e to the negative number. No, it's not going to be e to the negative. It's going to be just a negative number. But I can't take the ln of a negative number, so I actually have to consider because ln can only apply between 0. So I don't need e to, I do need e to a negative number, which is really a number really close to 0. This whole thing will be a big negative number. 3 plus a negative number is still a negative number, so it's going to be negative here. And then if it makes sense to you, as this gets bigger, this is going to be positive. Okay. The other way you can think of it is the shape of ln is always looking like this, right? So there's going to be a portion that's negative and a portion that's positive. Even if I scale and shift up vertically, that's still going to happen. A negative portion and a positive portion. So this is concave down. This is concave up, like this interval. And then here is a point of inflection. Okay. So find the critical numbers for the following functions and use the second derivative test to classify as a min, max, or neither. Okay, so this is a different way of finding mins and maxes. Is we simply find our critical numbers for the. This is again back to the first derivative, because I'm trying to determine whether I have mins or maxes. And so if I draw a picture of a min or a max, in both cases the derivative is 0 or undefined. Those are my critical numbers. But rather than doing a sign test, which is whether or not it goes from positive to negative or negative to positive, if I can look at the second derivative and say, like, well, if it's concave down and it's a critical number, it must be a maximum. And if it's a critical number and it's concave up, then it's a minimum. Okay, so first I want to find critical numbers. That's where the first derivative is 0. That's 2x minus 2 is equal to 0. That happens at x equals 1. Okay, and then rather than doing a sign test, like we would do for a first derivative test, I compute the second derivative, and that's just equal to 2. Okay, so it's always concave up, x equals 1. And so which picture does that look like? Well, the slope is 0 here, and the second derivative is positive here. Right? Because concave up is second derivative is positive. So x equals 1 is a minimum. And that should make sense to you because this is a upward facing parabola. So, I mean, that would be the minimum. So I actually do remember, I think these problems are identical to actually the previous sets of problems, I guess. But you could do a first derivative test on these and you would find the same thing. Okay, so first derivative of x. To find the critical numbers, I want the first derivative 0. That's when I'm trying to find mins and maxes, right? 3x squared minus 1, when that's equal to 0. So that means 3x squared is equal to 1, x squared is equal to 1/3, x is equal to plus or minus root 1 over 3. That's equal to plus or minus root 3 over 3. Just to rationalize the denominator, if you wanted to just do that. Okay, so I have those two possibilities. So I have x is equal to positive root 3 over 3 and negative root 3 over 3. So now I need to compute the second derivative. Second derivative would be 6x. Okay. And so when I plug in positive root 3 over 3, it's greater than 0, so it's concave up. And when I plug in negative root 3 over 3, when I plug in a negative number here, this whole thing's negative, right? So this is concave down. And remember, I drew my picture. When it's concave up, like this, then that makes this a x equals root 3 over 3 is a minimum because it's concave up. And x equals negative root 3 over 3 is the opposite because it's concave down. It looks like that. And this is what concave down looks like, negatives. So this is a maximum. Okay, so that's how you use a second derivative test. I simply look at, I classify my critical numbers by simply looking at whether it's concave up or concave down. Now, if the second derivative is 0, it's inconclusive. The test tells you nothing about it because you cannot use the concavity for whatever reason to classify that point. And that does happen sometimes. Okay, so let's look at this one. F prime of x is equal to x cubed plus x squared minus 2. And I want to know when this is equal to 0 to find mins and maxes. Okay, so this one's a little bit tricky. We're going to have to do a little bit of like estimating on factoring. And if you remember your synthetic division days or however you want to do this, you're going to have to try a few. I'm going to try the factor -1. So this is 1, 1, 0, -2. I'm going to do like synthetic division for this. You can use your calculator also. -1, 0, 0, 0, 0. Nope, that's not going to work. What about +1? +1 would be 1 times 1 is 1, then 2, then 2, then 2, then 2, then 0. Okay, so x minus 1 is a factor. And then it get x squared plus 2x plus 2 is a factor. Now, let's just confirm. If I were to FOIL this out, I would have an x cubed, then a 2x squared minus an x squared. That'd be a positive x squared. And then I have a 2x minus a 2x. That'd be 0x, and then a minus 2 there. So that works. So it is equal to this, and I want to know when this is equal to 0. Now, that happens at x equals 1 or when this is equal to 0. But by quadratic formula, if I look at if you remember my discriminant, right, because it's the b squared minus 4ac, that's 4 minus 4 times 1 times 2, that's 4 minus 8. That's negative 4. It's less than 0, so this has no solutions for this. This is like the quadratic formula would not tell you. So this can never be 0. So really, this is my only critical number here. And then I look at the second derivative. That's 3x squared plus 2x. And I want to calculate what happens at 1. I get 3 plus 2, that's equal to 5, and that's greater than 0. So this critical number is concave up. Concave up looks like that, so that makes x equals 1 a minimum. Okay. Let's do the same thing here for this equation. First derivative, 4x cubed minus 12x squared plus 12x minus 4. I'm going to factor out a 4. I'm going to get x cubed minus 3x squared plus 3x minus 1. Yeah. And I believe x minus 1 will be a factor, so I can try 1. 1 minus 3, 3 minus 1. 1, 1, that's negative 2, negative 2, that's 1, 1, 2, 1. Yeah, so I can factor out an x minus 1. So this is going to be 4 times x minus 1 times x squared minus 2x plus 1. And this is x minus 1 squared, so this is really 4x minus 1 cubed equals 0. So x equals 1 is my critical number. And then I use the second derivative test to classify it, to decide whether it's a min or a max, or neither. Second derivative of this is going to be 12x squared minus 24x plus 12. And when I plug in x equals 1, I'm going to get 12 minus 24 plus 12, and that's equals 0. So this is inconclusive. See, this is the second derivative test is not sufficient for me to tell whether this is a min or a max. And if you get an answer like that, if you wanted to really classify whether it's a min or max, I would have to revert to the first derivative test and look at the slopes to the left and the right. Equals 0 does not mean neither. It could still be a min or a max, okay, and that's a key part. And I'm going to use the first derivative test here. So if I have x to show you that this is definitely one of them, I haven't calculated which one it is yet. So the first derivative is definitely 0 at x equals 1. And so this is what the first derivative looks like. It's this equation. Well, if x is less than 1, this becomes negative, and negative cubed is negative, so it's negative here. And if x is bigger than 1, this would be positive. And so this goes from negative slopes hitting 0 slope and then going to positive slope. So this is definitely a minimum. But note that the second derivative test did not conclude that it was a minimum because it's inconclusive. You don't want to say that it's neither. Neither means that in the first derivative test it could be the same sign. Inconclusive just means the second derivative test has failed and it cannot classify the point for you. Okay, and that, like I said, that can happen, and this is an example where it happened, where you need to revert to the first derivative test to actually classify it for you. So in general, the first derivative test is more powerful. It's more useful in more cases and will guarantee an answer. But sometimes it's just tedious to do the first derivative test. It's easier to do the second derivative test for whatever reason. It's more convenient. Okay. So for this one, I'm going to say f of x is equal to x squared plus 1 to the negative 1. And that way I can do, you could do quotient rule. Like I said, we've done these problems before, but I'm just going to simply do my power rule with chain rule. The inside's not x, so I applied the power rule there. The inside's not x, so I got to do 2x there. So this is going to be negative 2x over x squared plus 1 quantity squared. And so when is that equal to 0? Only when the numerator is 0, which is x equals 0. And then for the second derivative, I'm not going to redo this because I already did the calculation before. I'm going to scroll up to see what we did for this because we repeated this problem right here. The second derivative was this equation right here, right? Negative 2 times negative 3x squared plus 1 divided by x squared plus 1 cubed. Okay, and then I want to evaluate at 0 what, so this is my critical number, what the second derivative would say. This is 0, so that's positive 1, that's negative 2 over 1, it's negative 2, that's less than 0, so it's concave down. Okay, that's what a concave down looks like. And the critical number is the derivative 0, so that makes it a maximum. Okay. And then for this one, first derivative of x is equal to cosine x minus sine x. I want it for critical numbers, I want the first derivative equal to 0. So I want when is cosine x equal to sine x? You can either use unit circle between negative pi, which is negative pi over here, all the way to positive pi. That occurs at this point and this point, because that's where the x value and the y value are here. And so this occurs at negative 3 pi over 4, as well as positive pi over 4. Okay, so this is x is equal to negative 3 pi over 4 or positive pi over 4. Okay, so those are my critical points. The second derivative is equal to the derivative of this, which is negative sine x minus cosine x. Okay, and so when I take the second derivative, negative 3 pi over 4, sine is negative, so negative sine is a positive number, minus cosine. Cosine is also a negative number. Minus that would make it plus a number. So this is going to be greater than 0. And the second derivative of pi over 4. Sine and cosine are both positive in this case. So this is a negative minus a negative. That's less than 0. I don't need to compute the exact number. I just didn't care what the sign is. So when it's concave up, so these are my critical points. So x equals negative 3 pi over 4 is a min. And x equals pi over 4. Because it's concave down, it is a max. And then we're doing a few more here. So f prime of x, product rule, is going to be x squared times 1 over x. Actually, to shorten these, because I don't want you guys to necessarily have to see me do it since you just saw me do it, or you can go back to these. The first derivative was x plus 2x ln x. And 3 plus 2 ln x. So I'll try to remember that. First derivative was equal to x plus 2x ln of x. And the second derivative of x was equal to 3 plus 2 ln x. So when is this equal to 0? Well, I want to factor out an x. So I'm going to get 1 plus 2 ln of x is equal to 0. That happens at x equals 0, or it happens when this is equal to 0. That's 1 plus 2 ln of x equal to 0. That's ln of x is equal to negative 1/2, or taking e to the both sides to get rid of the ln, that's x equal to e to the negative 1/2. So these are my two points. Now, one thing to keep in mind with x equals 0s, though, is that, actually, I don't know, like, ln of 0 is undefined, so I don't think the function is defined here. So I don't think you can use this. Yeah. It might approach that point, but it's technically undefined at that point because I can't do ln of 0. So this is not within the domain. And so I really only need to classify this point. This is my only critical number. Actually, first derivative undefined. Oh, no. The first derivative is 0, but the function itself is undefined. So it can't be a min or a max if it's not in the domain of the function. So with e to the negative 1/2, I'm going to plug it into here. So 3 plus 2 ln of e to the negative 1/2. Ln and e cancel, so this is 3 plus 2 times negative 1/2. That's 3 minus 1. It's equal to 2. It's greater than 0. So that means this is concave up. That makes it a minimum. Okay. Now we're doing some that I haven't taken the derivative or second derivative of before, so I have to. Now we're doing it with symbolically. First derivative, I'm going to write this as a x squared plus b squared to the negative 1. So that way I can do my power rule. This is going to be a times negative 1 x squared plus b squared. Subtract 1 is negative 2, and times 2x, the derivative of the inside. We're going to assume a and b are constants in this case. So this is going to be negative 2ax over x squared plus b squared squared. Okay, and when is that equal to 0? That only happens at x equals 0. So now I want to compute the second derivative. In this case, I'm going to do quotient rule just to change it up a little bit. So I'm going to do the bottom, which is x squared plus b squared squared times the derivative of the top, which is negative 2a, minus the top, which is negative 2ax, times the derivative of the bottom, which is 2 times x squared plus b squared to the first power by power rule. and then times 2x, and then divided by the bottom squared. Now for this one, the reason I do it this way is because I only care about the sign. So if this is positive, I really don't care about it, because that means the top will dictate what the sign is. This is a positive number. When I plug in 0, this is a positive number. This is a negative number. So this is a negative number. This becomes positive here. X equals 0 makes all of this 0. So if the top is negative, f double prime of 0 is less than 0. Here's my critical number, and because it's less than 0, it's concave down. That makes this a maximum. And then last one here, f prime of x is equal to, derivative of sine is cosine. Leave the inside alone. But the inside's not x. I got to multiply by the derivative of the outside, which is a. So I want to know when this is equal to 0. Okay, and so that happens when cosine of ax plus b is equal to 0. And cosine is 0, well, at a lot of places, but at pi over 2 plus every multiple of pi, like here and here. So ax plus b is to equal pi over 2 plus some multiple of pi, some integer multiple of pi, plus or minus. And so ax is equal to pi over 2 plus or minus k pi minus b, and then I divide that by a. So x is equal to pi over 2 plus or minus k pi minus b divided by a. Okay, these are all my critical points. And then the second derivative of this is equal to the derivative of this. I leave the a out in front, and this would be derivative of cosine is negative sine ax plus b. But because of the cosine, this side's not x, I gotta multiply by the derivative of the inside, which is a. So this is negative a squared sine ax plus b. And another way to think of it is that, the ax plus b had to be these points here, right? And so when I do the sine of ax plus b, sometimes they're positive, sometimes they're negative, right? So let's just do pi over 2 and 3 pi over 2 for the sake of simplicity. If this part is pi over, so the actual value of x is going to be pi over 2 minus b over a, and it's also going to be x is equal to 3 pi over 2 minus b over a. And so when I plug it in here, at pi over 2, or at least ax plus b is pi over 2, it's positive, so this is negative. So here it's the second derivative is less than 0. Here the second derivative would be positive because the sign value, this sign would be negative, times a negative would make it a positive. So that makes this one a, because it's negative, so it's concave down, so this makes this a maximum. And this is concave up, so that makes this a minimum here.